Hyperbolic trig functions are very similar to our regular trig functions. We already saw that we kind of defined them in a very similar way, where we had the hyperbolic tangent defined as hyperbolic sine over hyperbolic cosine. And things like the hyperbolic secant, cosecant, and cotangent were also defined in a similar way to our regular trig functions. Well, also kind of following suit, there are a lot of interesting identities that are can be proven to be true when working with hyperbolic trig functions. You'll see here that I have listed out 5 of them, but they kind of come in 2 pairs, or 2 groups, I should say. So these first identities up here, what we typically refer to as even and odd identities. That is, what happens when I go to one of these functions and I plug in a negative x value? How does that relate to plugging in just the same but positive x value? Like, what if I plugged in -1 versus +1? How does the answer change? Well, you'll notice here that with the hyperbolic cosine, whether I plug in something like -1 or +1, -2 or +2, I always get the same answer. There's kind of a symmetry in the graph. When I take a look at my hyperbolic sine, I see that this is what we would call an odd function. Because the 2 items don't match perfectly, one needs to have a negative put on it in order to make both sides match. Now, with numbers 3 through 5, these might seem very, very familiar because these are similar to the Pythagorean identities that we have for regular trig functions. You might recall that the cosine squared of an angle plus the sine squared of an angle was equal to 1. And you'll notice that here we almost again have the same exact basic format, except here I have a subtraction. You might also recall that with these old trig functions, there were 2 other identities that looked very similar to this. Now, I do not have those identities memorized, and so if you don't know them off the top of your head, I wouldn't worry about it. But you should be able to create these identities if and when you need to. Remember that if you were to divide everything here by, say, a cosine squared, you could see that you would end up with a 1 plus a sine squared over cosine squared would be a tangent squared, and 1 over a cosine squared would be a secant squared. Here's another important Pythagorean identity. And again, very interestingly, the same behavior occurs over here when working with the hyperbolic trig. I could generate something similar to this last identity by instead going to my first identity here and dividing everything by a sine squared. That would get me a cotangent squared plus a 1, and it would be equal to a cosecant squared of x. And I get the same behavior down here. So the nice part is that ultimately, if we can just remember in both of these cases the first identity, then we'll be able to create all the ones that come below it. So even for exams and assignments and things like that in this class, I would say that the only identity that you really need to know is this one, number 3. Because if you know that, then you should be able to create the other ones if need be. Now, since that is such an important identity, I'm going to take a look here to actually try to prove how that I know this is actually the case. How do I know that when I take hyperbolic cosine squared and subtract hyperbolic sine squared, I do indeed get 1? Well, the nice part here is that we actually can try to do this in the same way that we verified identities in a pre-calc class. We can start with one side of the equation and try to show that it can be transformed into the other side. Let's take a look at how we could do that here. I'll start by saying we see that the hyperbolic cosine squared minus the hyperbolic sine squared, I could go ahead and start to work with by going to the definitions of what these functions are. So notice that the hyperbolic cosine was, remember, e to the x plus e to the negative x all over 2. And if I want to square that, I can write this. I then want to do the same thing but with my sine. Remember, sine subtract, so I end up with this. And my goal is, of course, to show this turns into 1. Now, I can go ahead and start to square some of this. It's not too terrible. To square it, I can just go ahead and say, well, clearly I'm going to get something that's over 4. And then I can square the numerator. Notice this is going to be e to the x times another e to the x. I'm going to just quickly write it out up here, thinking about what this would look like. So if I have e to the x times an e to the x, that's an e to the x squared, or that's e to the 2x. I can then say e to the x times e to the negative x. Notice that's going to be e to the power of 0, right? Because I would add those powers up. But since I'm going to have two of those, I can write 2e to the 0. And then I'm going to have plus e to the negative 2x, because I'm going to have e to the negative x times e to the negative x. That's e to the negative x squared. Also the same as this. I can do something very, very similar over here. I'm just going to have minus, and I'm still going to have e to the 2x. I'm going to have now a minus 2 e to the 0, and a plus e to the negative 2x. Now, of course, over here, if I want to go ahead and combine these, I would have to take this negative and distribute it through. So what I'll see happens right away is that I'm going to have my e to the 2x and e to the 2x that are going to cancel out because of the subtraction. Same thing with my e to the negative 2x. However, the rest of my numerator is actually going to stay intact. Over here, notice I'm just going to get 2, and on this side, I'm going to have negative 2. If I add that up, of course, that's 4 over 4, and I do indeed get the value of 1. So this is 1. You could actually go through and verify or prove a lot of different identities, even more than just the ones that are listed here in the box. However, these are the ones that at least come up most commonly for us. Again, for exams and other assessments in this class, I really only think that you really need to have number 3 dedicated to memory, and that way you can use it, and you can use it to derive numbers 4 and 5 if necessary.